Well, thanks a lot, Emmanuel, for these very nice words, which mean a lot to me, in particular because they come from you, because you have these very high standards, and it means a lot to me. And I hope to come up with your high expectations with this talk on physical-chemical hydrodynamics of droplets in inkjet printing. So it's a subject which is both fundamental and applied at the same time. It's triggered by questions in applications, but it's really very nice fundamental science, and it's very close to my heart. So if you hear physical-chemical hydrodynamics, you immediately think of this famous book by Levitch, Physical-Chemical Hydrodynamics, and it came out in Russian in 1952, and the first English translation, it was 1962, and Levitch in his foreword wrote, "The book is an aggregate of problems dealing with the effect of fluid flow on chemicals or physical-chemical transformations, as well as the effect of physical-chemical factors of the flow." So here you see my own copy, heavily used here. And in fact, it's out of print. You can only get it secondhand. And I see that the price of this book is going up with time. So it's also an investment, but I'm happy to have it as book. So here you see Levitch, and Scriven in his foreword to the first English translation in 1962 wrote, "The book is the elucidation of mechanism of transport phenomena and the conversion of understanding so gained into plain useful tools of applications." Levitch on himself said that he would be an engineering scientist with a recognizable blend of applied chemistry, applied physics, and fluid mechanics. So plain useful tools of applications, where do they go? Well, thermal convection, paint and coating industry, spin casting, thin film solidification, nanotechnology and material science, droplet microfluidics, moving contact lines, and inkjet printing. So there we have a need of quantitative understanding. And I call this JFM type of fluid dynamics. But being here in front of one of the editors of Physical Review Fluids, I said, Physical Review Fluids is also okay, of course. So physical-chemical hydrodynamics of droplets in inkjet printing, we must think of not traditional offset printing. This is what you see here. It's very dirty and clearly not of the 21st century. So you must more think of machines like this, drop-on-demand inkjet printing. So you see this machine, which has technology in it, which we develop in our lab. And with this, you can print books on demand. So I have seen this machine operating. I mean, if the book is this thick, and they put in the PDF file, and they press, and then 30 seconds later, you have the full book nicely printed with cover and everything. I mean, it's just remarkable. And this is a type of printing we must think of. The core of this printing is this printhead, which you see here with supply, reservoir, and channels. It's MEM-based, so they made it out of one piece. And the printer has hundreds of them. And each of these has thousands of ink channels. So here you see it, top view, made out of one piece. You have 300 channels per inch, typically 10 picoliter droplet size, and typically now 50 kilohertz droplet frequency. The principle is shown here. You have an electrical signal here. This is transferred to some mechanical signal here. And this builds up the pressure with this piezo here. And the pressure then presses out droplets, which ends up on paper. And the paper moves at a relatively high velocity. So the jetting and droplet pinch off is seen here, and the degree of precision we achieve with our imaging is seen. So this is stroboscopic because it's so reproducible, and we really have resolution down to nanoseconds with this and to submicron. And this picture, in fact, was Nature Picture of the Year, and it came out from a collaboration with industry, which I think it's pretty remarkable. So inkjet printing is a difficult business because there are very fluid dynamical challenges. So you see here the parameter space Ohnesorg number, which basically is the droplet viscosity, and here the Reynolds number, which basically is the droplet impact velocity. I mean, there are, of course, further parameters like Deborah number and so on. I will mention this, but let's only focus on these two parameters here. And you see that the velocity or the pressure built up has to be large enough that you get jetting. On the other hand, if you're too large, then you get onset of splashing, which you don't want. If you're too viscous, you can't print. If you're not viscous enough, then you get satellite droplets, which are a mess. So you're a very small regime here. And the picture I just showed you is this point here, just in the middle of this printable regime. So there are further bottlenecks for printing. So you want an integrated approach. So you have the same ink on the printed side and on the side of the receiving substrate. And you have conflicting requests to this ink. So when you have to think of drying of ink, once the ink is on paper, you want this ink to dry quickly and immediately. And on the nozzle, you don't want it to dry. I mean, imagine this drop on demand, the nozzle is sitting idle for a while. And if the ink prints, it dries, or you get, in fact, clogging, and the nozzle doesn't work. So you must somehow balance between these two sides. So when you optimize the composition of the ink, you must really think of both sides, the printed side and the paper side. So there's Moore's law for inkjet printing, and this is what you see here. So not only Moore's law for ships, but also for inkjet printing. And what you see here is the writing system in millions of droplets per second versus time. And it goes up exponentially. So for every 30 years, the performance of these printheads, in fact, for the last 30 years, the performance doubles every 18 months. In fact, the slope is higher as compared to the ships. And this must go on, but it doesn't, this is not a law of nature. Of course, there's huge technology in here and science and development. And well, you want this to go on because of various applications where you want to push this towards. So you want to get faster and more stable inkjet printing. You want to better understand this colloidal interaction of pigments. You want to understand the role of the surfactants. You want to understand the film formation by evaporation and polymerization. You want to go to chemical drying. And what you also want to understand is the interaction of the droplet with the surrounding air. So this hasn't been looked at so much, but with these high velocities, you really get considerable airflow. And this airflow, which you then excite, interacts with the droplets, and often in a way which you don't want. And there, in fact, you get beautiful instabilities of these droplets, which are in a regime of Reynolds numbers of 100 or so. So it's also, you see vortex formation, so this also would be something for these institutes. It's beautiful instabilities which set in air. So for this talk, I identified 4 subjects on physical chemical hydrodynamics in inkjet printing. So here on the channel side, the channel flow and the meniscus dynamics right here, and in particular entrained bubbles. Then on the jetting side, right here, the jetting of these multi-component droplets. Then on the paper side or the substrate side, the complex wetting and spreading and coalescence of droplets, and finally the drying side and also the interaction with the substrate. So first on the flow, on the nozzle, meniscus dynamics, and on the entrained bubbles. What can happen is seen here. So you print, and then the nozzle plate here, there's some ink sitting on the nozzle plate, but here you get partial evaporation. right here. And when you partially evaporate your ink, you get a surface tension gradient. And in this case, the surface tension here is larger than here. This means that there are Marangoni forces pulling back this droplet to here. And sorry, here it's well mixed, and then you get this flow, and this flow takes along some dust particles. So this is what you see here. So here is ink on the nozzle, and this is sucking this in, and you collect dust particles. So these dust particles are a disaster, and I come to this in a second. But let's first look into this flow. So it's simply the balance of a Marangoni flow driving this due to this surface tension gradient, and Stokes flow, which wants to keep this droplet there. And you estimate this, basically it's dimensional analysis, with the viscosity and with the height of this film that you can solve easily. So the time goes, the distance here goes like time to the 1/2. The velocity goes like time to the -1/2. This is what you saw, that is getting faster and faster and faster. This is what you see here. So x as function of time. And here you see the slope 1/2, meaning this divergence in velocity. And this flow takes dust particles along. And clearly you don't want to print in a clean room. You have to cope with this. And once these dust particles hit the meniscus, you get structures like this. Here, the meniscus is disturbed by these dust particles, and then you can get an entrainment of a bubble in this channel. And I won't go into this because we already did this quite a while ago. This bubble in the channel is a disaster because the channel is driven acoustically, and this bubble grows by rectified diffusion. When the bubble is large, a lot of air goes into the bubble, because the bubble is large means low pressure, and you have this huge area of the bubble, a very thin monolayer, and the gas goes in. When the bubble is compressed, you lose gas, but not so much because the bubble is small. So the growth processes can overwhelm, and then these little bubbles grow from cycle to cycle to cycle, and then at some point, the pressure is not large enough to press out ink, but it only compresses this bubble, and then this thing breaks down. So what to do about it? Well, the nice thing is that you can use the actuator also as sensor, and you can hear when the bubble is around. And once you hear this bubble, you say, okay, turn off this nozzle, and then this process of rectified diffusion stops, and the bubble simply dissolves. I call this the Microsoft solution. So when there's a problem, turn off the machine, wait a minute, and turn it on again. And this works here because in this minute, the bubble dissolves. And in that time, the task of this nozzle is taken over by others. I mean, every single nozzle is computer controlled. And that is what my first PhD student on inkjet printing did, and we understood this. And this is now implemented in machine, which you saw in the beginning. And he, meanwhile, is big boss at this Canon company, and continues this collaboration because we really saw that the fundamental understanding of this bubble dynamics and entrainment process led to this much better product, which now is a cash cow for Canon for this printing on demand. So here you see the process in numerical simulations. How we do this, I will mention in a second. So at the top, we have no bubble. At the bottom, we have a bubble, and you see the bubble oscillating, and the pressure being partially absorbed by the bubble, leading to a much slower jet. Well, the larger this bubble is, of course, the worse it is. So that's the numerical simulation to give you some idea on how this is looking. So there are, however, also intrinsic meniscus instability. When is the air bubble entrained? And that we looked at with Paul Steen when he was on sabbatical in Twente. You get this intrinsic instability once you drive with too high frequencies and too large amplitudes, and you simply do this by linear stability analysis. And he had done in this beautiful paper linear stability analysis for the shape of oscillating bubble and made this droplet motion filling a periodic table. Very nice paper. And those methods we applied to our meniscus. And then we could identify modes which are non-axisymmetric. And this is, of course, which you don't want. You want an axisymmetric mode to jet straight and not under some angle. This defines this threshold. And they want to go faster, faster, faster. But here, again, it's a physical instability. It's fluid dynamical instability, linear instability in this case, which sets the speed of operation of the machine. And with this, it sets the price of the machine. So the price of the machine is set by a fluid dynamical instability, which I think is pretty remarkable. And the very same thing holds for the machines of ASML to make wafers, because there you have also air entrainment, and there also it is this physical or the fluid dynamical instability which sets the size of the price of the machine. I think it's very, very interesting and not appreciated, I think, by the general public. So further physical chemical problems at the meniscus, you have selective evaporation. So when the nozzle is idle for a while, you have selective evaporation, which changes the surface tension, the density, and the viscosity. And when you turn things on, you need a different pulse strength because it's more viscous than, or the viscosity changes. And of course, you don't want this. And we looked into this to counteract this loss of reproducibility, because of course, you don't want the pulse to depend on the time, how long this nozzle has been idle. So what we did is we jetted and let the nozzle open for some time from 10 to -3 seconds up to 10 to the 4 seconds, and then would look at the density of the drop coming out of the nozzle. And you could do so by shape oscillation. So we would have the drop, and the drop would then pinch off and oscillate, and we would look at this droplet oscillation, and from that we would deduce surface tension and density of this droplet. And from that we would be able to calculate the density and see. And you see that here the density is increasing with time due to the selective evaporation of the lighter component, and the heavier is remaining, and then things are totally screwed up. So now let's come to the jetting of multi-component droplets. We visualize this. And it's very small, 10 picoliters, about 10 microns in size, and they go to 10 meters per second. And it's non-trivial to visualize this. So 10 meters per second means 10 millimeters per millisecond or 10 micrometer per microsecond. And to visualize this is non-trivial. You need a temporal imaging resolution smaller than 100 nanoseconds. I mean, this is also often not appreciated. This, once you go small, you must go faster, faster, faster. So what we do is we combine the advantages of LED illumination, which is blurred, and laser illumination, which gives you this speckle and diffraction. And we have this illuminated laser-induced fluorescence, which with 7 nanoseconds pulses, we have incoherent fluorescence, which gives these beautiful pictures. And that had been developed in our group. With this, we do the stroboscopic imaging, stroboscopic because it's totally reproducible, and we can resolve, in fact, up to 10 nanoseconds in time and smaller than 1 microsecond, so 1 micrometer. And with this, we could, I think for the first time, visualize the hierarchy of breakups and this droplet formation. And there's this very famous paper by Michael Brenner and Sid Nagel. In fact, it's Michael's PhD thesis. And they looked into this pinch off, and they solved this with the slender jet approximation. So you will see Navier-Stokes equation in lubrication theory or slender jet theory for the velocity, for the thickness here, which is called H, well, that you solve with this boundary condition, and with this you get pictures or movies of this type. So here visualized with the photon camera, and here calculated with this scheme. But what, well, here is another case where we compare the numerical simulation with the experiments. The color code is the velocity. So here you see in the tail you have very high velocities because surface tension pulls this back. And here you could avoid the formation of satellite droplets. The tiny difference which you see here is due to air friction. Air friction there we didn't include. If we can include this, and then the agreement would be even better. But well, I mean, here we're in a regime where air friction is not particularly important. So in a sense, this is a digital twin, and this helps the company a lot because when they test new inks, they don't want to do the tests. They really want to understand where we go. So what you see here are, in fact, droplets with different viscosity from 5 millipascal seconds at the top to 22 millipascal seconds at the bottom. And you see that at the top, the surface tension is not enough for the viscosity to keep it together, or the viscosity is not enough. And you get this splitting, and you don't want this, obviously. So they could do these tests with this digital twin and then rule out those viscosity and go towards this higher viscosity inks. These satellites you want to avoid because they form this mist. This is what you see here. So here we now go to femtoliters satellite droplets. So you have this primary tail and you have a secondary tail here, which breaks up by Rayleigh-Taylor instability, and they produce this mist. And this mist is then evected away by the wind generated by the jetting process and ending up in random places on the paper, and that you don't want. So you want to really stabilize this. So here you see different visualizations with the Shimatsu, where you see both the primary tail, the secondary tail, and the ternary tail. Those hierarchy of tails have been predicted by Michael Brenner in his PhD. They follow from the slender jet approximation, but they had not been seen. But here we can go up to quaternary tail, which I think is pretty remarkable. And once this breaks up, of course, well, you have all these little dust particles around. So you want to make these tails as short as possible, and how to stabilize them. One is to go to more viscous ink, so larger Ohnesorg number, and this slows down these unstable modes. Another method is to play with the mode stretching to stabilize this, and I show that this works here. So here we have playing around with the viscosity. What I measure is the length of the secondary tail here, from here to here, for two viscosities. And you see that this higher viscosity up here is better because this tail is much shorter, producing less vis. So here we improve the situation by going from 5.6 millipascal second to 8 millipascal second. And this leads then to much less droplets, therefore to less contamination. You can also play with these pulses. So here we have two different pulses, trapezoidal pulses and multi-component pulse. And in this case, this trapezoidal pulse is better on printing. It means a considerable effect here. And if you're here, you basically don't get any secondary tail, but well, here it's in fact not so good. So this polluting mist can be controlled through the ink viscosity, which you do via temperature, and through the meniscus motion, which you control via piezo. What we are now doing is to add elasticity, viscoelasticity. So this is the third way to control this. And up to now, most inks are in fact Newtonian, but you can now start to play with non-Newtonian elements. And we add some viscoelasticity. So here, for this case, we add tiny amounts of PO. With this, we can stabilize. So here is pure water. Here, tiny amount of PO, viscoelasticity, and then this is fine. You see, the drop is kept together. you should be, of course, very careful, because here you add too much and then the drop is pulled off. So you don't want that, but you want to be in this regime here. So let's go to the third subject, the complex wetting, drop impact, spreading, coalescence, and drop film interaction. And as I know, Manuel is very fond of numerical simulations. I want to start with this numerical simulation here of the drop impact. It's done with the volume of fluid method and the Basilisk code developed by Stefan Poupinet and colleagues. Here you have drop impact with a Weber number of 40. And what you see is the impact, the spreading, and then the recoil, because in this case it's the hydrophobic substrate, and the takeoff. On the left, you see the local energy dissipation, and on the right, you see the velocity. Now we are interested in the force which this impact is causing. And we measure the force with a scale here, so a force sensor in experiments on the left, and on the right, well, measuring the force is easy. You simply integrate the pressure, and then you get this force. And this is what we get. So red, the simulations, and blue, the experiments as force as function of time. And this is a remarkable movie in many ways. So the first remarkable thing is that there's a perfect agreement. And I must say that the experimentalists with whom we did this didn't trust these little wiggles here. Oh, we don't know what it is. But the wiggles are real. These are these capillary oscillations. So you see that in the simulations, every single wiggle is reproduced. There is no parameter. I mean, we just calculated. And I mean, I was flabbergasted by this degree of agreement. And the second remarkable thing is that there's a second peak. I mean, of course, you would expect this first peak to happen, right? I mean, if the drop hits the surface, surely you get this peak as a force. But you also get a peak at recoil. So it spreads, it takes off, and you have this recoil, and this is the second peak here, which can be pretty pronounced. So this was at Weber is 40, but now let's go to Weber is 9. This is the situation here. First peak, we get these capillary waves, which have been seen before in this paper. And what you get at Weber of 9 is this air cavity. So the thing is closing, and you get this cavity here, and then, in fact, the liquid forms a singularity, and you get bubble entrainment. You get the second peak here. In fact, this had been first experimentally found in France. In fact, in Lyon, by Barthelot and Josserand, and Daniel Bonn, when he was still in France. So they found this experimentally first, but here we understand the mechanism. So it's really this thing closing and forming two jets, one jet going up and one jet going up, down. And you see that this jet going down is so violent that the second peak here is much more pronounced than the first. I mean, isn't it amazing? So it's this magical number, Weber number of 9. You have this impact, and well, you get a force peak, and then it spreads, and it comes back, then it takes off, and it is then this jet, and the jet hitting the surface causes a much stronger peak than the first one. I think it's just remarkable. And it is, interesting enough, easy to find. So here you see the bubble taking off, the droplet taking off with this bubble entrained. Yeah. And again, I mean, look at this degree of agreement. I mean, it's really very, very, very nice. Well, here you have the full thing for Weber is 9. If you go a little bit smaller to Weber is 7, the entrainment is gone. And if you go to Weber is 11, is also gone. If you increase the Ohnesorge number a little bit, even by a factor of 2, it's also gone. So it's a singularity where you have to be in parameter space, but it's relatively easy to find because these are the normal conditions. If you take a normal droplet, say millimeter size, and normal distance, say like this, you get this. So this is why Dennis Barthelot found it. And we had also seen it before, this Paisho and Amy Tsai in our lab. You get this droplet, this entrainment, because this is, so to say, the natural thing. And it's very funny that it is only at those conditions where it is there. So this is this paper which just came out earlier this year, and Watzel put in the scans, so here you can scan this and also enjoy the movies. Well, now it was the impact of one droplet, but there are many droplets, and on the effects of physical-chemical hydrodynamics. So once you have one droplet and another droplet of a different type, say different color, you get interaction, and then you get Marangoni forces. In fact, the force can pull this droplet over the other and coat it, and of course you get smearing. You don't want that. And you get droplet evaporation. And we know all this problem of the evaporation of a pure droplet with this famous coffee stain effect, a paper by Degen, which I think is one of the most influential papers in fluid dynamics over the last 30 years. Beautiful paper identifying the singularity at this edge here. So this enhanced evaporation, which transports all these colloidal particles here, leading to this coffee stain. But well, this is a pure liquid droplet, but now let's go to a binary droplet, and then you get Marangoni flow. And here I go to a droplet which is water glycerol, and then you get the following effect. So water is more volatile and it evaporates here more. Therefore, here in the liquid you have less water, here you have more water, and then you get a surface tension gradient in this direction, and you get flow in this direction, and you get flow like this, the Marangoni flow. And this affects, of course, the deposit. So here we play with the physical-chemical hydrodynamics, simply with the composition of the liquid and with the lubricant layer. And this is the deposit which we get. So this is pretty bad. We get coffee stain, we get stick, slip, and this kind of structures. Here we have water and a lubricant, and then everything is focused to the middle. This is what you don't want. You want something like this: water, lubricant plus surfactant, a situation like this, with more or less homogeneous distribution of the deposit. So how to calculate this? So on the numerical methods. What we used here is finite element method, the arbitrary Lagrangian finite element method. There's a beautiful code made public, written by Andrew Hazel and Matthias Heil, the object-oriented multi-physics finite element library, OMFLIP. And it's mesh refining here, and it can follow this interface. And with this, we can very conveniently implement these Marangoni forces. So these are the equations for the pure droplets. Navier-Stokes water concentration is outside and diffusion outside. So we really solve inside and outside. We have a stress boundary condition, and in particular, we have the kinetic boundary condition. So the evaporation is given by the concentration gradient right here. And that we implement, and we now see a pure water colloidal droplet. And you see indeed the coffee stain effect with the stuff going here, the colloidal particle, and here the deposition is formed. And you get this coffee stain. So this is for the pure droplet, and we can really reproduce this very, very nicely. But now we go to multi-component droplet. So from water, we go to water glycerol, for example, and then we must put in the concentration field, the water concentration field, which is given here. And what you also must put in, how surface tension, density, and viscosity and diffusivity depend on the water concentration. But this is all very well known. I mean, you look up in former days, you would look up the CSC handbook, but now you look up in the internet. So with the older people, you can still estimate the age of the scientist by looking at this bookshelf. What's the edition of the CSC handbook? Well, these days you look it up on internet. This is all very well known, and this we implement and solve, and then we can get situation like this. So for this binary droplet, and I showed you those experimental results before, but this we can now simulate: glycerol, water. And you see that here the flow structure is totally different, and we get this deposit in the center here, so that we really can reproduce. It's pure physical chemical hydrodynamics. But there's more than Maragoni, also gravity, and this came as a huge surprise to us. So what we teach to our student is that once the bond number is small, gravity doesn't play a role. So the bond number compares gravity with capillarity, and if this is smaller than 1, let's forget about this. This is all textbooks, so Gary Leal's textbook, everything says this. Let's forget about the gravity once the bond number is small. This is wrong, as we will see. And the reason is the selective evaporation. So because of you have selective evaporation, say water glycerol, you create a density gradient. And this is what you see here with the sessile droplet. When we have a cross section here, we see the flow is going inwards. And when we have the identical droplet, which is pendant, and look here, it goes outward. So gravity must play a role. Well, the reason is this rho, this convection rho, which forms. So here going inwards and here going outwards. And we visualize this role from the side. And this is driven by density differences emerging by selective evaporation. So it's not only Maragoni flow, which emerges, but also buoyancy-driven flow. And they are in competition, and this you will see. So we simulate this. So here you see numerical simulation for sessile droplets giving this role, and then the numerical simulations for pendant droplets giving a very different role. And well, here we compare very, very different roles. So in fact, when we simulated this first, we of course didn't include gravity, because we said, well, I mean, bond number small, gravity not important. And we saw in experiments something very different. So it's always important to do experiments. And then well, we thought about what's going on. And indeed, it is gravity which does play a role. So sessile droplet flow like this, pendant droplet flow like this, and the parameter controlling this is the Archimedes number. So the Archimedes number, you could also call it Grashof number. So Jacques Magnodet calls it Archimedes number. Well, I think it's fine. I mean, it's dependent on the community. So it's nothing else but Rayleigh over Prandtl. So Grashof, by the way, did quite a bit. He is kind of forgotten. He was professor in Karlsruhe in the late 19th century, and he did quite a bit. I mean, of course, not at the level quantitatively as Lord Rayleigh, but I mean, philologically, he saw quite a bit. So when we now reduce the Archimedes number from Archimedes number is 4, where gravity does play a role, to Archimedes number is 0.5, you see quite some differences. So here, pendant and sessile droplets are very different, whereas this difference is gone for these small Archimedes numbers. So here it's just the same pattern, and well, clearly, once you go to very small scale, gravity can't do much. And this is this paper with Yaxing Li, who was a PhD student on this project. He is now a postdoc in ETH in Zurich. And there was a paper in parallel by David Ferrest and co-workers, and they found basically the same at the same time, totally independent. They use different liquids, they use different methods, but the main message that buoyancy matters is also in there. Yaxing was, I mean, he in another paper, he was faster than others. Here he was slower. So in fact, ours came out a few months later as these others, but well, it was already accepted and so on. And then we saw this coming out. He was very unhappy. It's like Yaxing. This, I mean, it's on the science, right? And it only shows that it's relevant. It was, so to say, in the air, and it was independently found in Nottingham, and with us, it only shows it's a relevant subject, and so to say, was mature to be discovered, and it only shows relevance, so all is fine. So you can go to a more general conclusion, namely that both Maragoni convection and gravitational convection is relevant, depending on the parameter space. And then we analyzed together with Christian Dittens, who did the numerics. And what I will now show you in parameter space of Rayleigh versus Marangoni, how the quasi-static flow pattern looks like. And so up to now, I showed you the evaporation of the droplet as function of time. Now I will show you the quasi-stationary flow pattern as a function of the parameters. And it's quasi-static because evaporation is slow as compared to the time scale it takes to develop this flow. So quasi-static is totally justified, and we double-check this. So I will now move in parameter space here. And now you see that very soon, when you increase Marangoni, you get both rolls. Marangoni rolls here and Rayleigh rolls here. Now, parameter space, you decrease the Rayleigh number, and you have pure Marangoni flow right here. With negative Rayleigh, you go here. And now you get in this regime where you have pending droplets and both Marangoni rolls and Rayleigh rolls. And now you go back. So pendant droplet dominated by gravitational buoyancy. Now we go back in parameter space, and we go now to this interesting regime, Marangoni versus Rayleigh. Here they compete. Now Rayleigh wins here, purely buoyancy driven. And back to sessile droplets. And now it comes again this most interesting regime where you have both rolls, so in between these lines. And now finally Rayleigh wins. So I think it's pretty neat. And it of course depends on contact angle. So here we see this for contact angle is 60, where you have dominance of one or the other. When you go to contact angle, it's 120. Things are of course different. So they look like this. You can, by the way, also, this is what we are doing right now, you can also go to negative Marangoni number. And I will come to this. So negative Marangoni number means that, that the role of evaporation and the emerging gradient in surface tension due to selective evaporation is turned around. And the situation will be much worse and much more complicated. I will show you. So this is this case here. So this is, so to say, negative Marangoni number. It's a binary colloidal liquid where the less volatile liquid has a larger surface tension. This is the case water ethanol. So here you have more evaporation of ethanol. This means that the water concentration is higher here than here. And this thing now pulls in this direction. So it's the other way around than this guy. And what you get, and here's the experiment, is this. You get axial symmetry breaking. So the other case is always axial symmetric. Here, axial symmetry breaks. And, well, volume goes down as function of time. And, well, first, very quickly, because all ethanol goes away. And then later, water goes away. And the axial symmetry is reestablished once the driving is not strong enough. So here in this regime, we have a laser on, and here we calculate the average vorticity from these pictures as function of time. And you see very strong symmetry breaking, but at some point it breaks down because then it's small enough and it stabilizes again. So what you also see is that thermal Marangoni flow doesn't play a role because it's still evaporating and you have evaporative cooling. You would expect that there is some thermal gradient, but what we, in most cases, what we find is that solute Marangoni flow is always stronger than thermal Marangoni flow. And we now compare the experiments where this axial symmetry breaking happens with the numerics here. And this is the result. It's the average spatial average vorticity as function of time. Again, no parameter. And this is what we get in experiment, and this is simulation. So this strong axisymmetric breaking behavior happens. And we know also now why it happens, the Hopf bifurcation. I mean, it's really very beautiful. And well, then here it comes down again. So we have now these three cases of droplet evaporation: pure liquid droplet, binary liquid colloidal droplet, where more volatile liquid has a larger surface tension, and then binary colloidal liquid, where the less volatile liquid has a larger surface tension. Those three cases. But I would like to come to a fourth case, where we look into the ternary colloidal droplets. And this is an alternative way to prevent the coffee stain, namely by self-lubrication. And various applications, the paradigmatic ternary liquid is ouzo, which you all know. Well, we're in France, you know it under pastis for the French, and it's also well known here in the lab. And as you see here, so I took yesterday with this pastis here. We want to see the physical chemical hydrodynamics. So we take some pastis or ouzo, put it in here, and then we add water, and we get this nucleation of all these droplets. So what happens? So Tuan made this nice animation. So water, anise oil, and ethanol are perfectly. Water and anise oil and ethanol are perfectly miscible. So water and anise oil not, but if you add sufficient ethanol, they are happy and it's all soluble. If you now add more water, the solubility of anise oil goes down and you get this oil droplet nucleation. So this becomes unhappy. And here you see the ternary diagram determined by titration. Here you have 100% ethanol, 100% anise oil, and 100% water, and you start here with ouzo or pastis and go in this direction. And this is a phase separation curve. So in principle, here you would have two phases, the oil phase and the water phase, but here you get this ouzo regime. Here. So here, these little oil droplets, they emerge and they give this milky structure, which is so typical when you add water to your ouzo. And we now take such an ouzo droplet and add particles, and this is what we get when we let it evaporate. So it's now a ouzo suspension on an arbitrary surface, and we don't get a coffee stain. And the reason why we don't get a coffee stain is that we get this ring formation here. So these oil droplets form, and the oil droplets then coalesce. They form a ring on a surface, and this ring decouples the rest of the liquid from the surface, and the particles are left in the evaporating surface and are put together in this way. So this is what we get out of this. This supraparticle which forms, and we cut this with focused ion beam cutting. This is the structure. So it's a porous structure which we can create in this way. So here we zoom in down to 100 nanometer. And we understand this in detail, how these particles arrange and how also the arrangement of the particle depends on the time scale. So this is this case where we have self-lubrication with ouzo plus nanoparticles forming these supraparticles. If we leave out the oil, we get this kind of structure, so this coffee stain. And if you leave out the particle, of course, we only get this oil droplet here. So really, you combine these two things, and in this way, you avoid the coffee stain and can create these supraparticles. So this self-formed oil rings has this crucial role in preventing the coffee stain. So we call it self-lubrication here. So this is the ouzo case, the contact area. Contact diameter goes down because of this formation of this ring, and then rather getting the spinning and this coffee stain, you have self-lubrication and you end up here. Here with confocal microscope where you really see the ring. So the yellow thing is a separated oil, and this really protects the surface of the deposit. So it's pretty neat and very relevant in material science to make substrates like this in an intelligent way. Well, the final thing is the ternary liquid, where we study the Leidenfrost effect. So, well, some of you may know, in particular, Henri, we're obsessed with the Leidenfrost effect. So you all know the Leidenfrost effect. You have a hot substrate, you pull on a droplet, and this droplet sits there forever, not forever, but for very long, because it's thermally decoupled. So here you have your droplet, and it's supported by this vapor layer, which thermally protects this droplet so that this droplet lives for very long. And it has first been found by Johann Gottlob Leidenfrost, professor in Duisburg, whom you see here. Unfortunately, I didn't find a more friendly picture of him. But Leidenfrost is well studied also in France by David Queré. Unfortunately, I did find a more friendly picture of him here. And he wrote this nice annual review of fluid mechanics on the Leidenfrost effect. So what we decided is to do Leidenfrost with Ouzo. It's simply taking our Ouzo drop and putting on there, and then we find this very interesting thing. So what we find is, of course, because of selective evaporation, first ethanol goes, and then we got in this droplet, evaporating droplet, we get oil, all these oil droplets, tiny oil droplets, and they coalesce, so they get larger, larger, larger. So here you have this coalescence, and at some point, they form a film around this droplet, and this is happening here, and this film prevents evaporation. So this Leidenfrost droplet basically kills itself because what supports him is the vapor, and once you have the oil film wrapped around it, there's no vapor anymore because this oil doesn't evaporate so easily. And here I show you this last two stages of this droplet. Here, the Leidenfrost droplet, where the oil is already fully wrapped around, and also here it's wrapped around, and it loses its support, and then the touchdown is unavoidable at some point because the vapor is all gone, and once it's touched down, it takes off. So I think it's pretty neat. Good. So I think I have entertained you, I hope at least, with various physical, chemical, hydrodynamic challenges in drop-on-demand inkjet printing on the nozzle side with air entrainment, on the jetting side, on the impact side, and also on the drying and evaporation side here. If you want to read more, I wrote this annual review of fluid mechanics, which came out last year, 2022. And I put major work into this, and I hope you enjoy the reading. And also, we wrote this physical, chemical, hydrodynamics of droplets out of equilibrium with Chouard, who is a chemist. And there are many more examples on nice and surprising phenomena where we now get the grasp on. So what we see is that the gap between what can be measured and what can be simulated is closing. We also see closing gaps between fluid dynamics and neighboring disciplines, such as chemistry, colloidal science, chemical analysis, lab on a ship, microfluidics, catalysis, electrolysis. I mean, this bubble formation electrolysis, I mean, it's all along this thing, also catalysis. I mean, it's all physical, chemical, hydrodynamics. So these fields, I think, offer great problems to fluid dynamics. They have extremely rich phenomenology and multidimensional parameter spaces. And I think that this field offers excellent examples to learn how to decipher often surprising and counterintuitive phenomena. It is an excellent training ground for young scientists. Much, much better than, say, a high-energy physicist. I hope there are some high-energy physicists around here. So, I mean, they get very selective training, right? I mean, they either go to this huge detector and this huge screwdriver entertain themselves for years, or the theoreticians, they calculate these Feynman diagrams. There's hardly any interaction, and they don't see the success so quickly. But here you have this little tiny problems, say evaporating droplets, and you learn a lot. You learn how to do clean experiments. You learn to set up clean experiments, right, to identify it to the core. You learn image analysis. You learn modeling. You also learn simple numerical simulations, and all connected. I think it's an excellent training ground. And well, what I talked about is, of course, the collaboration over many years with many people. Well, it started all with Jos de Jong here, who I mentioned before, who is now big boss at Canon with his inkjet stuff. And well, over the years, many have contributed. So Michael Rumpf, she just finished her PhD and just started at Canon. And well, various colleagues and staff with whom I enjoyed collaborating over the years. And with this, I would like to end. So this is a collection of nice movies of this physical, chemical, hydrodynamic phenomena, and I'm happy to take questions.
Thank you very much. We will go for questions. Basic question on the piezoacoustic excitation. It's sinusoidal. Can we change the shape?
Well, yeah, we play with the shape. Yeah, I mean it's not sinusoidal. No, I mean it's we play with the shape of the pulse, and in fact, it's more trapezoidal. So like this. But we play. I mean, this is a very important parameter, and it's a parameter to play with. I mean, in former days, we would not be allowed to play with the ink composition because this was declared holy. And then this was the shape of the pulse was one of the very crucial tuning knobs where we could affect the jetting. And in fact, I showed you these two simulations with two different pulses, which would lead to a very different secondary tails, and therefore a very different amount of contamination by mist.
The Leiden first, why did the bubble explode and not go back to Leiden first?
Well, it explodes because it's all wrapped by oil, and then what happens is that the oil doesn't evaporate, and then you have to touch down, and then of course you get boiling, and then you get this huge bubble inside the drop, and this leads to the explosion. I mean, your colleague Henri has experience with this because he did the same in a different context. So this is then this explosive growth of a boiling bubble. So
contact before you can evaporate again.
Yes. I mean, it's this explosive evaporation. Yes.
So, okay, in your drawing, you suggest that the anise oil is totally wetting the drop.
Yes, it's wrapping it. Yes, it's fully wrapped. Yeah, it's fully wrapped. No, it's fully wrapped. The final state is fully wrapped. I mean, first it's of course at the outside, but then so much oil that it's fully wrapped, also from the bottom.
There's a total wetting of the anise oil on water.
Yes, and then water cannot evaporate, and well, then it's a very late stage.
That occurs close to the contact line because of the singular flux there. So if there is a little bit of anisole at the top of the
then it doesn't matter. Yeah. Sure. Yeah. I mean, this was also the so this was also here in the drawing. So here we have it's fully wrapped already here, and then it's still supported because it's boiling here. But in the very last moment where it's fully wrapped, it cannot support it anymore. Well, I mean, then the question is, does it bounce back? And then it very much depends on the parameter. So, well, the hydrophobic surfaces are, so to say, easiest to calculate because contact angle is 180, and there's always a thin layer in between. But once we have hydrophilic droplets, when it's wetting, I mean, we must, of course, put in some information on how the contact angle depends as function of time and space. So we must put in some contact line dynamics. So that's why, in a sense, the hydrophilic droplet is more complicated because we need this additional information on the interaction of the droplet with the substrate. And that we must tell the fluid dynamical equations, of course.
Finally, I did the relation with now all is very known. What are the open questions in the field?
No, I mean, it's not the case at all. So what you want to do is that you want to go to faster inkjet printing and to more control, to smaller droplets. I mean, here in the beginning, I tried to sketch open issues in this business here, bottlenecks for further progress. You understand that there are competing requests for the ink in the channel and on the paper, right? But you must overcome this, right? And you must find a good compromise. Or what's the optimal composition of the ink? So there are new regulations. So what drives it, interesting enough, is regulations. So right now, many inks have some organic component which is evaporating, but legislation doesn't allow these organic components anymore. So Canon, in fact, for this printing is in some trouble because their cash cow ink will be forbidden by European Union legislations in a few years. And then they must come up with an alternative ink, which is similar quality, but doesn't have these volatile components. So you want to go to more viscous inks and still print. So what you would like to do, in fact, is what? And of course, then you must carry this on. Right? I mean, you don't want to stop. If you would stop here, well, I mean, this would be then saturated, but you want to continue here, print different materials, particularly non-Newtonian. I mean, non-Newtonian inkjet printing is totally open. I mean, this one movie which I showed, where we have a small Deborah number, elasticity, I mean, this is only the beginning. So you want to go to ink with some elasticity. You want to also to go to more viscous inks here. So you want to push this in this direction here. Now, these are all challenges here. So surfactants, where very little done is the interplay between surfactants on the surface and in the bulk. I mean, this is strongly stretched. I mean, I call this also a rheometer for these liquids because you really achieve extreme stretching. So if you do it in the standard rheometer, you achieve some shear, but by far not as extreme as here. And you want to understand the role of the surfactants for this printing. How fast is the diffusion of the surfactants on the surface as compared to the exchange of the surfactants with the bulk? I mean, there are tons of open questions. So. Sorry? Yes. Yes. Yes, I mean that's another problem which is pretty open. So this paper is porous material, and then in fact it partially intrudes, taking the pigments along, and you get clogging in the paper. And I didn't address this here, but it was in our program. We also look into this, well, there's in fact fluid structure interaction. So as we all know, the paper wiggles when it's wet. How does it happen? You want to avoid this, and how deep do these pigments go into the paper? I mean, all these are very interesting and relevant questions. Also, what's the role of elasticity there? So, I mean, clearly, future inks will have some elasticity. I mean, they complicate things quite a bit, And everyone who has worked with PO knows that this is pretty difficult, and particular reproducibility is an issue. But we will have to go to inks with some elasticity, but in a controlled way.
Is the first water larger as evaporation or for the paper?
It very strongly depends on the paper. So I mean, there's these shiny papers, and I think you can't generalize. I mean, there are of course papers which really suck in a lot of liquid, and then it all goes in, but in the end it will evaporate. So in the end everything will evaporate. But the ratio of well, how long this will take strongly depends on the paper. They have various papers. They have names for these papers, how thick they are, porosity, and so on. And it's a huge zoo of different papers, and it very strongly depends. What they also do is now they apply 2 layers. So they first have this one wetting layer, and then on this wetting layer they put on droplets. So what's very relevant for them is capillary waves on these very thin films. So they first wet that the next droplet with different liquid, in fact, the next droplet is then interacting in the way they want. So it's beautiful physics, beautiful fluid dynamics, and full of fundamental questions.
Okay, so let's thanks Detlef again.